Alright, so I'm just going to continue from where we left off in the last lecture. In the last lecture, we considered a game that looked like this with the payoffs. When you put P2's payoff here, P1's payoff here, these are average payoffs over the history of the game. We're considering an infinitely repeated game, and we're considering a discount factor that's arbitrarily close to 1. So it's very, very close to 1. So think something like 0.99999. So with that kind of discount factor, and with the game being like this in structure, you could sustain 3-0, where player 1 gets 0, player 2 gets 3, or where player 1 gets 3 and player 2 gets 0, just by playing CD or DC forever. It's feasible, it's not equilibrium, but it is feasible. And so we talked about what's feasible, and we talked graphically about what can be sustained in an equilibrium. So let's formalize what can be sustained in an equilibrium a little more in this video. How do we formalize it? So first we say that what we know from the graph is that, from our previous lecture and from the graph, is that you could sustain anything in here, in this green region. As long as it's strictly more than 1, 1, it can be sustained in equilibrium. So just pick a pair of payoffs. So for instance, just to concretize things in your mind, let's say you want to offer player 1 1.2 and player 2 1.3. Some numbers that are greater than 1 and 1. Okay. If you want to give these two players 1.2 and 1.3, then there has to also be some sequence of actions, of action profiles, right? Some sequence of outcomes that can generate that. Let's call those outcomes B1, B2, up to B something, basically, because it will keep going on after BK, let's just say, keeps going on ad infinitum. These are average payoffs, so this is like the average of what they get over all of the periods, and it can be sustained by some series of outcomes. A strategy which can help sustain this is a strategy where, for player I, Si, given some history, h1 up to ht minus 1, so this is the strategy about what, which defines what player I should do in time period t, equals either bit, where the player I just continues with this outcome path, this specified outcome path, which gives these kinds of payoffs at the end, if h r j equals br for all r equals 1 to up to t minus 1. Create a partition here. Right, so if the other player has been following this strategy in the past, then you follow it, otherwise just play D. So an example could be, let's say we want to show 1.5, 1.5 for each player. So just alternating between CD and DC, right? In every alternate period, I would get 3, in every other period you would get 3, and then when you get 3, I get 0, when I get 3, you get 0. And so for both of us, our average payoffs would end up being 1.5, 1.5. And we're happy playing this alternating game as long as the other person keeps doing that. And it's under a threat where otherwise we would end up playing D, right? And then both of us suffer. And so we wouldn't allow that to happen. So then, once we establish this, what we've shown is a folk theorem. We've shown precisely three things, and I would write it on the board, but it's better if I just show you on the book. So this is proposition 435.1. It's on page 435, and what it says is three things. One is, for every discount factor, any Nash equilibrium that we sustain here has to offer both players at least what they would earn from deviating forever. So at least 1 and 1. So whatever we sustain has to be at least that. The second thing is, for any of the points within this green region, as long as it's not on this line, as long as you pick those 2 points such that each value is greater than 1 strictly, you can find a delta, a level of patience, such that that outcome can be sustained as an equilibrium outcome. So if it's, for instance, 1.01, 2, it's grossly unfair to the first player, right? You're just offering that player slightly more than 1. But if that player is patient enough, then you can sustain this as an equilibrium. You can also sustain 2, 2, that one's easy, so on. And then the third thing this says is that you will always still have a Nash equilibrium where the outcome is dd in every period. It is still a Nash equilibrium. Yes, you have a whole lot of other Nash equilibria that are possible, but dd forever is also a Nash equilibrium. If the other player is playing d forever, irrespective of what you do, then your best response is also to play d. Okay, that's the end of this video. See you in the next one.